Hi everyone, I'm Lucas, and this is Mahir, and we're from Team 8393, the giant Diencephalic BrainSTEM Robotics team. So I'm one of the lead designers, and Mahir is a programmer on our team, and we're sort of going to go through the robot and explain how we balance between design optimizations and program optimizations to account for whatever is on our robot. So to begin with, I'm just going to do a brief overview of what our robot does in a big picture. So first, going with the drivetrain. This year we utilized the Rev mechanical wheels, so about 3 inches, and they're powered by a bevel 16-to-1 motor. We also utilized 3 linearly sprung odometry modules, 2 parallel, 1 perpendicular, for accounting for position on the field during auto. Then, sort of just moving into our scoring mechanisms, we start with our collector. So our collector is just a standard claw. We utilize two 3D printed parts with rubber bands in the center to account for the curvature of the cone to maintain that robust grip. We then have a 4-motor lift that's able to launch the cone to its final destination very quickly. We also have a mini servo turret up top. It's able to go to any direction, and an extension. So we can basically just deposit from wherever we are in the field, whether that be in teleop or in auto, for the perfect placement of the cones. So the first thing I want to talk about is sort of something that we do every season and that we think is essential to have success, and that is a design iterative process. So for us, this means that at the beginning of the season, we design multiple approaches to every subsystem in CAD right away. So we'll have multiple people designing their different ideas, or maybe we'll just have smaller different fixes for each subsystem. And so once those are all designed, we're able to easily manufacture them quickly and inexpensively out of materials like wood, so that we can load it quickly, we can test, and we can evaluate whether or not this is minimizing our scoring cycle time, which is the sort of target metric for if we want to use the subsystem or not. Once those designs prove themselves, we can then transition into more robust materials, such as FR4 or plexiglass laminate, which is all the black material that you see on the robot. Or this year, we also use some aluminum. So we use aluminum on our lift slides and the base plate for our turret. And so we use this just for a more robust connection, and we're able to thread it so that reduces more space as well. And so when it comes to the iterative process, there's also another step that really adds ease of use, and that's balance between simplicity and modularity. And so when I say modularity, I just mean the ability for you to remove a component out of the robot really easily, so it's able to be fixed if it gets broken, or if you have a new design that you want to test out really quickly. It's not optimal to have to redesign the entire robot for just one subsystem. So if we look at the pictures that I'll be sharing, we start out with just the base of our robot. So this is sort of the empty shell, if you will. So this is the drivetrain and the odometry by itself. And as you can see, we have a base plate and we have 2 walls that have mounting holes. And so this sort of lends us into the first step of the modularity, which is the lift. So the lift, hopefully you can tell on the sides, has tabs, and it uses Rev nut strips. So we're able to slide it into the side panels and attach it with 4 screws on each side. And then we also have a maker beam frame that surrounds our 4 motors, which allows us to use 4 screws from the bottom to attach it. So we have 3 sides of attaching, but it only uses 12 screws. So we're able to easily remove it if something happens, such as if the string snaps, we need to replace that, or if we need to replace a slide. The next subsystem that uses modularity is our rotation system and just central structure. So this system just needs 8 screws to be removed, 4 from each side of the lift, and then the entire system can be removed. Within the system itself, the turret can also be removed with only 4 screws, and the extension can as well. And then finally, we have the collector, which also can be removed with simply 4 screws going into some Go Build quad block mounts. So, and the really nice thing about this is that we're able to swap out for alternative designs, such as this old collector that we had. We can easily replace it with the existing extension without having to make any modifications whatsoever. And so now that I've talked about simplicity, modularity, and iterations, I'm going to sort of focus on one subsystem in particular that really added the biggest advantage for our robot this year, and that's our 4-motor lift. So this year we had 4 5-to-1 motors that are all geared together for our lift. And so then we had 2 extension pulleys to power the 2 sides and 1 retention pulley in the center to pull it down. And so this allows us to launch the cone to the high junction in under 0.7 seconds and really just gain that speed advantage. And so I'll hand it over to Mihir now to begin talking about the optimizations that went into that.
Yeah, so the main goal of our software this year was to maximize the potential of our subsystems while also accounting for the nuances of our robot. Looking at the lift in particular, you can see that it's a very complex mechanism that has a lot of nuances. For example, when the lift goes up, it requires more force the further it goes up. So what we used to account for this was a PID controller where the proportional part would smoothen out the movement of the lift, and the derivative part would account for the change of error over time, where if the change in error slowed down, an additional power would be applied so that the lift would maintain good speed at higher heights. And then the integral part, which would allow the lift to get to the desired position and add more power if it wasn't getting to the desired position over time. Another part of our program that we try to optimize in particular is time. So we use video analysis throughout the season to look at our autonomous and see where our robot is pausing, where different actions can be parallelized, or other optimizations. So Lucas can show a video of our early autonomous in the season. So you can see here that the robot is quite, it has a lot of pauses in its movements. And throughout the season, we optimized it and found ways to maximize the mechanics of the robot, which you'll see in our MTI submission, where we got a 1+5 autonomous high pull, where we took many videos throughout the season, looked at where we could lower time. And one specific example was whenever we were initially trying to do our 1+5 autonomous, we had a robot move all the way to the wall and then try to pick up cones. But we found that we could actually optimize this by maximizing the potential of our mechanics and extending our extension before we reached the end of the wall to grab the cone instead, which we found was much faster and saved a ton of time in our autonomous. And
yeah, so that was an overview of our robot and the programming and the optimizations that sort of mix those two together, and sort of just the things that we learned and what we find is really critical for every year, regardless of what the challenge is. So we'll open it up to questions now.
Yeah, our first question coming in from Screen 404. Did the strategy change throughout the season, and how did it affect changes on the robot's hardware and software?
Yeah, for sure. So at the beginning of the season, one, I think, critical component of strategy, which I think many teams saw, was the circuit itself. And so at the beginning of the season, we found that we wanted to go for the circuit in every match, no matter really how competitive it would be. So our robot was immediately designed to be able to move around the field very, very quickly and deposit on any pole, regardless of its location. Now, the strategy as the season moved on sort of turned to just, covering opponents' cones, because as the matches became more competitive, circuits became less viable, and, just doing it sort of wasted the points on the field. So in terms of changes to the design and to the software, we didn't make a ton of changes because we found that the mobility is still critical and the flexibility of depositing on any side and distance is still critical. It's just a matter of, where we're actually placing those cones now.
And we also wanted to find ways to improve upon our robot, especially in our autonomous, where we, at some point in the season, we kind of saw that we were reaching our maximum potential using the mechanics of our robot. So we wanted to achieve better results. And the way we found we could do this is by adding this pole aligner, which was actually a very late change in the season that allowed our autonomous to be much more consistent. So just finding new ways to optimize the mechanics to better suit your strategy is what we focused on too.
I think one thing I didn't mention as well with the robot is that we have these cone flippers that we added pretty late in the season. But we found, as matches became more competitive, as I mentioned earlier, it became critical to have every single cone deposited exactly where you need it to be. And if you drop the cone, that could often, be the cause of your loss. So we add these cone flippers because in many of our matches, like there were fallen cones, whether it be a result of us or our alliance partner, and the ability to correct those mistakes and place it somewhere was really critical for us.
We got a couple more questions coming in. Quinn McGinley, I'm going to expand on your question here. They asked, how can you afford to keep all of your robots like that in the background? Because you got a very impressive background. But I think more importantly, can you maybe just talk a little about how your team does fund development and how do you maintain your finances and fundraising, that sort of thing?
Yeah, so I think just largely we have over time we've accumulated resources. So we have our own laser cutter in-house that we've had for probably over 10 years now. We have a CNC router. So we have machinery. We also have parts that we've accumulated over the years, whether it come from sponsorships directly from companies or money that we've received that we use to purchase these parts. So most of the parts that, especially on this year's robot, we actually didn't need to purchase new. We've actually had in stock, like within our shop. But in terms of how we fundraise, it sort of comes in different parts. A lot of it does come from sponsorships and just reaching out to companies in our area. So we present at conventions. So we do lots of outreach with these companies, have calls, and they're all very interested. Like it's really easy to get, especially engineering companies, to be like thrilled about the work that first teams are doing because they wish that they had the opportunity whenever they were younger to do it as well. So using those connections. And then also just at our outreach events, we have fundraisers, whether it be just like small things like concession stands or 50-50 raffles, all together throughout the season, it adds together and we're able to do stuff like this.
All right, we're going to have to go a little speed around. We got a couple more questions coming in here. One from C-League asking, given the modular hardware subsystems, do you time yourselves to see how quickly you could swap in a replacement module?
I think so. I'm not going to say for 100% certainty that this is true, but throughout the season, we had to remove the lift many times as we were iterating upon it. And I think over Thanksgiving break, we were having, some time crunches before our first qualifier. And I think we got it down to like 15 minutes to remove the entire lift, restring both spools of the entire lift, and put it back in completely so we're able to program it again. So, yeah.
All right, last question we're going to take here from Terry Faber. Besides the awesome robot drivers, what would you say is the primary reason BrainSTEM has been the Pennsylvania State Winning Alliance for the past 5 years?
So I think it comes, as you said, with the drivers. That's obviously one really critical role. Our past driver who just graduated this year, Nathan, shout out to Nathan, was the driver and he won for the past 5 years. So that's critical, just the experience that comes from that. But also, again, like with the iterative process, making refinements to the robot that can be easily tested and really quickly, fixed on the robot that allows us to have maybe a V2 or a V3 by states even. And so that sort of step up and, change in our robot is really critical.
Awesome. 8393, thank you so much for telling us more about your robot. And if you are watching live, by the way, we're going to have 19458 equilibrium.exe coming up in just a little bit. But 8393, good luck into the center stage season. Thanks a lot.
Thank you.
Thank you.